Hi, everybody. Welcome to this lesson on earthquakes. Today, we're going to discuss faults and folds and how those features form. Now, at any type of tectonic boundary, there's going to be forces involved. We talk about convergent boundaries coming together, divergent boundaries pulling apart, and transform boundaries sliding past one another. And rocks in this process are being squeezed and stretched and ground apart. And that's what we mean by stress, any type of force acting on the material. And strain is the change in shape that occurs because of those stresses, those forces. Now, strain can mean maybe it stretches and it doesn't return back to its original shape. Or maybe it returns back to its original shape, it acts elastic. You can see off to the right-hand side, there's a graph that kind of shows you how materials behave. You can think of a rubber band. At first, that rubber band acts elastic. It stretches, and if you let it go, it'll return back to its original shape. But there will be a certain point where if you stretch that rubber band enough, even when you release the tension, what's going to happen is it's not going to return back to its original shape. It's going to be a little bit longer than when it started. And if you continue to stretch and stretch and stretch that rubber band, eventually it reaches the point of failure or fracturing and breaking. And rocks do exactly that same thing. Rocks store energy through what's called the elastic rebound theory. You can think of a ruler, you can think of an elastic band, but eventually they store energy by stretching, and once a section of that rock breaks, the rest rebound back to their original shape. And that rebounding, that release of energy is what causes our earthquakes. Rocks can behave two different ways. They can either just break, or they can flow kind of more like a putty or a dough. At high temperature, rocks are going to flow. At lower temperatures, they're going to break. Breaking is when we produce our faults, and at higher temperatures, when rocks flow, we produce what's called folds. This experiment kind of shows you what would happen to a marble cylinder under low pressures and temperatures. Low pressures and temperatures, the rocks act brittle, they break. And at high pressure and temperatures, rocks will actually deform and bend. If you can't put your finger on the fault, you can't identify it. In the picture on the right, hopefully you can identify where the fault is. A fault is where movement has occurred between rocks. If you compare the layers on this diagram, you can see that they're separated. They were once one continuous layer that went all the way across the diagram. And you can see how they're being almost look like they've been cut in half. And right along here, that is our fault, that boundary, that break between the rocks. There's some terminology we're going to use when we discuss faults. The hanging wall and the footwall. And remember what we discussed in class. The rule is draw a stick figure. Their belly button goes right on the crack, the fault. Their head will go straight up above, and their foot will go straight down below. The side where their foot is called the footwall. The side where their head is will be called the hanging wall. And that becomes very, very important if you want to identify what has happened in the past. Normal faults are where the hanging wall, where their stick figure's head would be, has dropped down. They're the result of tension. You'd find these at divergent boundaries. And reverse faults are where the hanging wall, or where the head was, has moved up, and these are formed by compression. It produces shortening of the crust. Hopefully you can identify the faults. I'm going to talk about these in class, but I don't want to do it now because I want you to have a little bit of practice. See if you can identify the normal and the reverse faults. Strike-slip faults, the most famous one is the San Andreas fault. This is where they're sliding past one another. You'll notice that the fault isn't even. There's breaks and fractures, and they get hung up, they snag, and while they're sliding past each other, they're storing energy, and eventually they can release those in large earthquakes. San Andreas fault is an excellent example. Even here in New Jersey, we get earthquakes. Now, we're not by a convergent, divergent, or transform boundary, but we were at one point. And those faults, those breaks in the rocks are still here in New Jersey. And occasionally, they do have a little bit of stress on them. They slip and produce small earthquakes that sometimes people can feel. Now, when rocks act ductile or plastic, this is rocks that happen at high temperatures, and instead of breaking, They bend. You don't get earthquakes. Off to the right is a famous picture. This is a Route 23 fold. You can see how the rocks, they were once flat layers, have actually bent like sheets of paper. Really interesting. This was because of compression. And these turn out to be really important features for trapping oil and natural gas. What happens is we get impermeable or solid rock bent up into what we call an anticline, and then gas and water will pool the top of that anticline right here, and we'll drill into that to siphon out the gas and oil. So this is an anticline structure. You can see that the rocks are bent up like an A. We have another structure called a syncline, and that's this U-shaped structure here. That's it for today. I hope it's been helpful. Take some notes on this. Be prepared to ask me questions about it later on. Thanks for watching.